All right, so the implicit and explicit methods are both first order accurate in the time dimension, which is a bit problematic. So we can now look at another method called the Crank-Nicholson method, and that is an alternative to the implicit scheme that is second order accurate in both space and time. And essentially it means the Crank-Nicholson method is developed upon the fact that the difference approximations are developed at the midpoint of our grid. So in other words, if we have a space and time grid with the dimension, with the nodes I plus 1, I minus 1, at time t of n, tn plus 1, we take both the spatial dimensions at I plus 1, I and I minus 1, at time step n and n plus 1, and then we take the time values at n and n plus 1 to calculate the time value at t n plus a half. Okay, so in essence, all of these points surrounding the midpoint are contributing to the solution. Okay, and that makes it second order accurate. So, in terms of our time derivative, we have that, so day phi by day t. Now remember, we're deriving a solution for tn plus half, is approximated at phi I n plus 1 plus phi I at n divided by delta t. Okay, but now our spatial term is averaged across time steps n and n plus 1. Alright, so day squared phi by day x squared can be approximated by a half multiplied by phi n I plus 1 n minus 2 phi I n plus phi I minus 1 n. And separate these, so delta x squared plus phi I plus 1 n plus 1 plus minus 2 phi I n plus 1 plus phi I minus 1 n plus 1 divided by delta x squared, which when we substitute back into our equation, we get our diffusion equation, we get negative lambda phi I minus 1 n plus 1 plus 2 times 1 plus lambda phi I n plus 1 minus lambda phi I plus 1 n plus 1, which is equal to lambda phi I minus 1 n plus 2 1 minus lambda phi I n plus lambda phi I plus 1 n. Okay, where lambda again is equal to k, our diffusion coefficient, delta t, delta x squared. Okay, so what do we do with this equation? Well, we formulate a set of simultaneous equations, and we solve that set of simultaneous equations. So effectively what we would have is we would have our coefficients augmented by the values at our grid cells, so phi, say 1, 1, phi 2, 1, for example, and that would equal to our boundary conditions. Okay, and what happens is that you actually end up with a tridiagonal matrix, which becomes relatively easy to solve using some type of iterative method. And again, we would apply our boundary conditions to this formulation as per the previous methods that we've seen.